studying anthropoid primates, so that all primate species, well, not all, obviously, a selection of primate species that include monkeys and great apes, so also humans, and also their fossil relatives. So that's about 40 million years worth of evolution. So I've been doing my PhD since 2016, so I've been part-time. The Australian National University.
Amazing.
So in Canberra here, yep. So we didn't have anyone in the country who did anything like what I wanted to do. So I had to go get external supervisors from other countries. So my primary supervisor is in the US, David Polly, Professor David Polly at Indiana University in Bloomington. And he's been helping me with sort of the evolutionary side of things, with methods and analysis, and also sort of coaching through drafting papers. And my associate supervisor is Dr. Emiliano Bruna, so he's in Spain, and he works at the CINEA. I cannot say it in Spanish, but it was a specially built research institute for a fossil site in north of Madrid. So he's particularly interested in brain evolution in the human sort of clade, if you like.
Amazing.
Yes. So my chair of the panel is Alison Behe, who is say Associate Professor Alison Behe. We're not big on titles in Australia, so we just tend to drop them off. So unlike the US, we don't always refer to our professors as professors. They're more like first name basis. So it's very casual. But yes, Alison is a fieldwork primatologist, and she is our head of school. So she runs the primatology research group, of which I am part. She's one of my chair of panel who overviews the entire PhD process. The main goal of my PhD was predicting the temporal lobe of the brain from the what's called the middle cranial fossa, which is part of the middle cranial fossa. Is this area. You can see there's like a hollow in here, and it stretches back here as well. So this is the side of the skull with the top taken off, and I can show you this digitally as well. And the half of the brain, which is the temporal lobe, is this area. So it fits almost perfectly like a sort of a cup into that middle cranial fossa. So 20 years ago, a paper came out saying that modern humans, you and I, have temporal lobes that are far larger than they should be for an ape or a monkey of our size. So no one had ever actually tested that since. Everyone's been doing sort of work with fossils and lots of imaging and lots of assumptions. So the temporal lobe itself is involved in memory, in the auditory process, for like hearing. It's involved in your parts of your how you associate things. In humans, it's involved in speech, but not like the actual function of speaking. Speaking, that's a little speaking. Tell it's like speaking. It's involved in like associated words. So shoe and sock, and so it's involved in really sort of complex how you associate things, and it does the same thing with objects. So it's sort of a huge area, which has over time in evolution gotten bigger and bigger compared to the rest of the brain. So my research was first to quantify statistically using MRI scans of 12 different primate species, including humans. So everything from humans, gorillas, chimpanzees, capuchins, and take the volume of the temporal lobe, so the size of it. Sure. Okay, so this is a transcut. The cranium removed on a female chimpanzee. So landmark protocol was based on covering as much area of repeatable points that we could find on each cranium across 12 different species. So obviously the cranial shape is quite different from, chimpanzees to squirrel monkeys, and I'll show you a human too in a minute. So this covers the furthest reach of the temporal lobe, and the temporal lobe fits into this area in here. This would be the front area of the temporal lobe, and this is more or less where it comes to the edge of the midline of the skull. So it doesn't come all the way to the middle. It comes sort of tucks in, and it comes in just in a just within that area. So these were the 7 metrics, and I'll find a human to show you the sort of difference in the shapes that we're dealing with, but that all those points are still there and still easy to see. So all these marks are left by the temporal lobe itself. So that's sort of how closely it fits within the cranium. And so that was in designing my protocol. What we did then was, because we couldn't rely, as I said, almost all fossils. I bring up a brain as well. You can see the temporal lobe is this area here. So you can see it stretches all the way back to here, which is sort of quite far back in the brain. And then it comes around. This is only half a brain, but you can see where it tucks under at the front, and it doesn't reach sort of the middle. So I had to design, just stop sharing, I guess, for the moment. I had to design landmarks which would be able to be used on broken skulls as well. So those that might be missing, often with fossils, you might be missing the front because some of these regions are really delicate. And you might not have all the area, all the points that you need. So we transferred them into millimeters. So instead of doing, so that we had 3D landmarks if we ever wanted to do geometric morphometrics, but also transform them into 2D, two-dimensional millimeter measurements from point to point. And then the goal was to see if statistically I could predict the true temporal lobe volume, which we knew from the MRI of the brains, from the skull of the same species, from CT, and sort of each metric which was more reliable than the other.
When
Um,
you say reliable, well, I'm just curious, like, how has your checkpoint experience been, and how has it helped you collect data? I'd love to hear like your
yep.
checkpoint journey.
Definitely. Um, so yeah, it's been fantastic really, because without a quick really high visual, so like a lot of the other programs that I've tried, they can be a bit clunky. The sort of the ease with which I can manipulate a skull or a brain or whatever. Because I've also done landmarks on brains in another paper. For I did the methods and analysis design for a colleague's paper. So sort of the ease with which you can do that with really big data sets is
Uh,
probably the best thing that I've had about it. Um, not being and sort of being able to visually see something so clearly. And also the function with being able to sort of turn it, like 75%, 25% on the visual scale, so that I can make it sort of semi-transparent,
mhm.
the surface semi-transparent. That allows me to also, when I'm landmarking on the inside of the skull, to check where points are sort of on the outside. So something may look right. Some of those landmarks are suture points that correspond to one on the outside,
Uh-huh.
and being able to just switch it to a 75% view lets me know, how exact I am in lining those up.
And when you use other have you used other software tools, and like how has Checkpoint compared, and what are the differences you've seen?
I've used Checkpoint honestly since 2015, 13, I think. My masters, I think I used it because it was quick and it was easy, and Landmark was my first um, sort of the original Landmark software, which is no longer in use,
Hmm.
um, was my sort of original starting point. And yeah, I've sort of taught students, taught other colleagues how to place landmarks. I suppose I have a high level of repeatability. So
Hmm.
a lot of people come and ask me to teach them, you know, how to place landmarks, what's a good place to put a landmark,
Hmm.
because it's both a statistical and a biological reasoning.
Uh-huh.
So it has to be repeatable for the not just the software, the analysis of the geometric morphometrics,
Hmm.
but it also has to be repeatable because it needs to be a biological point that exists across all species in the case of my research, and that included the fossil species. So even monkeys from that were originally in Egypt when it was a tropical rainforest um, were, had to have the same point so that I could predict temporal lobes. So for me, it's been amazing being
Awesome.
able to do those metrics. In this case, for my PhD, the first paper on predicting temporal lobe was highly successful. We were within sort of one standard error of prediction, which was for what we're looking at across so all 7 metrics. It was pretty good, more than pretty good.
Awesome.
So that's allowed me to go on and predict for broken fossils. So we're looking, we did a paper on Homo erectus and Homo ergaster, who were lived around 1.6 million years ago, one in Africa and one in Java. And we did sort of looked at width and length and ratios to see, in that case, you know, whether one might have a different size temporal lobe. And as it turned out, one did. So there is a difference. There was a species debate as to whether or not they're the two different species or one. That's just sort of changed over time with climate